Okay, next we move on to section 2.9, which is about molar mass. Molar mass introduces the concept of the mole, which sounds kind of silly. Why would we be talking about silly little burrowing rodents in a chemistry class? But actually, the mole is a very important quantity in chemistry. Basically, you're not going to go anywhere in this class or chemistry of any kind if you don't know about moles. And so just as an introduction, there are a couple of different ways that you can count large quantities of things. You can count them directly one by one, or you can count them by weighing them and dividing by the mass of an average item. And for instance, if you've got a bunch of eggs, you can always count the number of eggs, or you can actually instead, you can weigh them and then divide by the mass of an average egg. In fact, that second method seems kind of cumbersome, but that would actually be the easier way to do it if you have a very large number of eggs, say thousands of them, rather than counting all of them. Just weigh them and find out what the average mass of an egg is and divide by that, and that'll give you the number of eggs, at least approximately, which is probably close enough. And a method, it turns out that methods like that have to be used when you're trying to count atoms or molecules, because they're so small that there's no way that you could count atoms or molecules individually, even if you only had a few of them, because they're so small. It turns out, though, that because they are so small, that any quantity of atoms or molecules that would be substantial enough for you to even notice it or to appreciate it or to deal with it in any actual real life way, you would have to have an enormous, huge, unbelievably large number of those atoms or molecules. And so even if you were able somehow to count them individually, even a small sample of something like a handful of pennies, it would take you thousands of years to count the number of atoms of copper in that handful of pennies. That's assuming even if you could count individual copper atoms, because they're so small. And so what we do instead is we resort to what I was saying about a large number of eggs. Basically, you have to weigh the quantity of substance that you're dealing with, and then divide by the mass of an item of that substance, and that way you can tell how many items you've got. That brings us to the concept of the mole. Mole, is a funny sounding word, but it's just a quantity of items. And in fact, it's often called the chemist's dozen because it's a quantity of items like a dozen. Whenever you have a dozen of something, you have 12 of that item, whatever it happens to be. You could have a dozen of anything. Well, it's the same idea of a mole. With a mole, whenever you have a mole of something, you have a certain number of items. And just like with dozens, it's possible to have a fraction of a mole or more than a mole. You could have a half dozen eggs instead of a dozen. That's entirely possible. And the number would be half of 12 or 6. You could have 2 dozen eggs, or you could have 2.3 dozen eggs. Same with a mole. You could have half a mole, you could have 2.3 moles, you can have any kind of multiple of moles. The word mole itself is derived from the German word for molecular weight, which is something like molecular Gewicht, I think is how they pronounce it, or something like that. And so this is just basically a shortened form of that. In German, MOLE doesn't refer to burrowing rodents, and the word just passed into English unchanged. So we have a little bit of fun with it. The American Chemical Society has a mascot, which is a cartoon mole wearing a lab coat and safety goggles and all of that. They even sold stuffed animal versions of the mole at one time. So, you can have a little fun with it along the way, too. The number in a mole is very large. And that's large because atoms and molecules are so small. And the quantity is 214. One mole is equal to 6.02214 times 10 to the 23rd items, whatever those items are. For most purposes, 6.02 times 10 to the 23rd will suffice as being accurate enough. And so that's the number that we'll actually use most of the time. But if you want to be more accurate, you can always use that number. As I said, this, oh yes, and this is also known as Avogadro's number. Amedeo Avogadro was an Italian physicist who laid the groundwork for determining this number by working with gases around 1800 or so. Now, this is kind of an odd value for a number. You might wonder, why would they choose 6.02 times 10 to the 23rd? Why not something more easier to remember, like 10 to the 25th, or maybe 5 times 10 to the 23rd? Well, the reason this number was chosen is that it's the conversion factor between atomic mass units and grams. Okay, so that makes this a very important number and a very convenient number. So 6.02 times 10 to the 23rd atomic mass units would be equal to 1 gram. And grams are a convenient unit for us to use because they're big enough for us to appreciate and for us to measure accurately, and laboratory balances weigh things in grams. And so, in other words, 1 proton would have a mass of 1 atomic mass unit. 1 mole of protons would have a mass of 1 gram. And what this means is the masses in the periodic table become much easier to deal with. Because now the masses in the periodic table can be read as either atomic mass units per atom or grams per mole of atoms. And grams, again, are a unit that are easy to deal with. Another example. One atom of the isotope carbon-12 has a mass of 12 atomic mass units. 1 mole of carbon-12 atoms would have a mass of 12 grams. And so now if you can weigh the amount of carbon you've got, you can find out how many atoms you've got. If you want to find the mass of each atom, of carbon-12, then you can just take the mass divided by the number of atoms that have that mass collectively. So it's 12 grams per mole, but there are 6.02 times 10 to the 23rd atoms in a mole. So 12 grams divided by the number of atoms in a mole would be 1.99 times 10 to the minus 23rd grams per carbon atom. And that would be equivalent to 12 atomic mass units. Okay, so and remember that the mole is also a quantity that makes samples of atoms and molecules a reasonable size, not just a reasonable and measurable mass, but a reasonable size. One copper atom is way too small for you to see or to do anything with, but 1 mole of copper atoms would be about the size of 22 pennies. And that is something that you can actually see and appreciate and actually deal with, like if you wanted to do an experiment. That's an appreciable amount of stuff. You can weigh it fairly accurately, and so you can know how much stuff is going into the reaction. And so whenever you're going to try to find the relationship between a mass and a number of items, you're going to end up having to use Avogadro's number. And some examples follow. Some examples where we actually do that. Where we can actually convert between number of moles and number of atoms. Also note that MOL is the official abbreviation for mole or moles. You save a whole 1 letter. It's like using JUN for June, but anyway, it does save a little bit of effort, so I use that quite often. So just so you know. So if you want to convert between moles and number of items, it can often help if you think of what would you do if it were a dozen instead. Okay, so we know that 1 dozen is equal to 12 items. And that's your equivalence statement. So the conversion factors that would be derived from that would be either 1 dozen for every 12 items, or 12 items for every 1 dozen items. And you can use whichever one you need in order to make the units in your calculation work out correctly. So for example, if you had, say, 3.75 dozen donuts, how many individual donuts do you have? Well, clearly, if you got 3.75 dozen, it's just going to be 3.75 times 12. But I'm going to do it formally to show you how the units work out. So you can use it as an analogy when you're working problems with moles and atoms or molecules. And you'll notice that dozen donuts by itself is equivalent to being in the numerator. And so dozen donuts on top here will will cancel with dozen donuts on the bottom there, and you end up 3.75 times 12. And that comes out to be 45 donuts. Or on the other hand, if you have 27 donuts, how many dozens of donuts do you have? Okay, well, we're going the other direction, so we use the same conversion factor, only upside down. So if we have 27 donuts, and we know there's 1 dozen donuts for every 12 donuts, donuts cancel as a unit, and we end up with dozens of donuts as the unit remaining. And 27 divided by 12 is 2.25. So 2.25 dozen of donuts. Doing the same thing with moles, your conversion factor is going to be, well, your equivalence statement is 1 mole of any kind of items is equal to 6.02 times 10 to the 23rd power individual items. That means the conversion factor is going to be either 1 mole for every 6.02 times 10 to the 23rd items, or 6.02 times 10 to the 23rd items for every 1 mole. And so when you're converting between items and moles, this is one of these two conversion factors will be what you want to use. So let's say, as an example, say you have 3.75 moles of iron. So how many iron atoms do you have? Well, it's just the same idea as what we did up above here with 3.75 dozens. Number of dozens times the number of items in a dozen. Down here, it's going to be number of moles. Fe is the symbol for iron, so that's why I'm writing that. Times the number of items in a mole. Moles of Fe will cancel, and 3.75 times 6.02 times 10 to the 23rd ends up being 2.26 times 10 to the 24th iron atoms. Okay, big numbers, but that's to be expected because atoms are really tiny. Another example, say if you have 27 atoms of iron, how many moles would that be? Well, in this case, you just use, again, the same conversion factor, only it would be upside down. "27 iron atoms, and there's 1 mole of iron, or anything else, for every 6.02 times 10 to the 23rd items, iron atoms in this case. And Notice that iron atoms will cancel out as a unit. And mathematically, all you end up having to do is take 27 divided by 6.02 times 10 to the 23rd. Do be sure, though, that when you divide by a number in scientific notation, you put it into the calculator inside parentheses. So this should be 27 divided by, open parentheses, 6.02 times 10 to the 23rd, close parentheses, then hit equals. If you do it that way, you will get 4.49 times 10 to the minus 23rd mole of iron. If you don't put parentheses around the number in scientific notation that you're dividing by, the calculator will misunderstand what you're trying to do, and you'll end up with a power of 10 that's way, way off from what it should be. Okay, so do keep that in mind. And also, in fact, far more often, we're interested in converting between mass and number of moles. Because really, in practical terms, there really isn't much application in chemistry for knowing the individual number of atoms of something that are involved in a reaction. We would really much rather know the number of moles. And so going between, say, just a minute. Mass and number of moles. Yes, okay, we did that. Yeah, so being able to go between mass and number of moles is much more important. And so it is possible to count by weight if we know the mass of 1 mole of the items that we're concerned with. Guess whose neighborhood has garbage day today? So the masses in the periodic table are equal to the mass of 1 mole if read in grams. Okay? And this is known as the molar mass. Molar mass just means the mass of 1 mole. And the formal statement of what molar mass is goes like this. An element's molar mass in grams per mole is numerically equal to the element's atomic mass in AMU. In AMUs per atom. So, well, it's just another way of saying that the atomic masses in the periodic table can be read as AMUs per atom or grams per mole of atoms. So essentially, same thing. So in other words, silver, according to the periodic table, an average atom of silver has a mass of 107.87 atomic mass units per atom, or 107.87 grams per mole of silver atoms. And so the conversion factor for going between mass of silver and moles of silver would be either 107.87 grams of silver for every 1 mole of silver, or 1 mole of silver for every 107.87 grams of silver. And you'll find that the masses of the elements can vary widely, of course, because the difference from one element to another is the relative number of protons and neutrons and electrons. And protons and neutrons are the heavy parts of the atom, so every time you add more, you gain more mass. And every time you go from left to right on the periodic table, one space, you're going to be gaining at least 1 proton, and probably some neutrons too. So that means a mass gain of at least 1 AMU per atom and at least 1 gram per mole for each space left to right. And so you end up with some atoms that are actually pretty heavy. Some examples of using conversion factors like this. Say if you had 500 grams of pure silver, how many moles would that be? Okay, well, that's simply a case of taking the 500 grams that you had and using the conversion factor between moles and grams. This one is going to be the one that has grams of silver on the bottom, because you want grams of silver to cancel. And this is equivalent to being in the numerator. And that's 1 mole. You want moles of silver on top of the conversion factor because those are the units you want to end up with. Let's see, grams of silver will cancel out. And mathematically, all you have to do is take 500 divided by 107.87. That would be 4.64 moles of silver. And you might also want to know how many atoms of silver was that. In order to go from mass to number of items, you have to go by way of moles. So now that we found the number of moles, we know the number of items in a mole. And we can find out how many items that is. That's 2.79 times 10 to the 24th Ag atoms. So that's how many would be in 500 grams of pure silver. Okay. On the other hand, if you had 17.5 moles of pure silver, what mass would that be? Okay, so you'd use the same conversion factor we used in the first part up above, only it's going to be the other way around because we're going in the opposite direction in terms of the units. So 17.5 moles of silver, and we know there's 6.02 times 10 to the 23rd. That's 23 there. Atoms in each mole. Moles of silver cancel, and when you multiply that out, you get 1,888 grams of silver. But that becomes 1,890 because of significant figures. You should only have 3 significant figures because of the 17.5 and the 6.02. So technically, it should be 1,890 in grams. Okay, and let's see. One last example. Let's see, if you have 1.94 times 10 to the 24th atoms of silver, what is its mass? Remember what I said, anytime you're converting between mass and number of items, you always have to go by way of moles. So the first thing you want to do here is find moles of silver. So we've got 1.94 times 10 to the 24th silver atoms. And there's 1 mole of silver. For every 6.02 times 10 to the 23rd silver atoms. And where am I here? That's 3.222 moles. Then we can take the 3.222 moles and multiply it by the atomic mass. Because we know how many moles we've got and we know how much each mole weighs. Moles of silver cancel out and we end up with 348 grams of silver. Okay, so those are some examples of those calculations. There are more obviously in the homework and some practice ones in the book that you can look at. This is, well, the end of this segment of the lecture, and also that's the end of chapter 2. So we'll be starting chapter 3 in the next segment in just a moment.